Today's podcast is presented by Podgo. Podgo is the easiest way for you to monetize your podcast, providing podcasters with a flat rate for ad space, so you always know how much you're going to get. So apply today, you become a member, and you can start reading ads as soon as you get accepted, and you get paid a flat rate within 24 hours. So make sure to check out podgo.co, that's podgo.co, and be sure to add our podcast in the How Did You Hear About Podgo section of the application.
It's the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode 38, where today we actually have quite an interesting history of physics episode, the Battle of the Approximations. Now, usually, or at least in our last History of Physics episode, we spoke about two scientists that, impacted physics or did something really crazy in their own field. But today, we're going to be talking about two concepts that kind of shook the field. The best way or the most efficient way to approximate functions. So today we have two different approaches, the Taylor approximation and the Fourier approximation. So we're going to be going through the history of them, how they're used in modern application and just, what they are, really.
Absolutely. And before we do get into that, we do have quite a bit of news, everybody.
Ooh.
So as you probably definitely heard, we are running a sponsorship on the podcast. So we might as well, we have the opportunity to run ads. So we will, and we will reinvest that revenue right back into the podcast to make it as good as it can be.
Of course.
Yeah.
That's the goal.
Yeah, and we also changed our official email. It is now math.physics.podcast@gmail.com.
Some very, very hype, amazing news. We recently, 2-3 days ago, we crossed 25,000 downloads.
That is right.
And interestingly enough, today, the day we're recording it, we're at, what's the number? I think it's 1984 Spotify followers.
Well, by the time this episode comes out, we're going to be over 2,000 followers.
That's going to be
Which
amazing.
is absolutely awesome.
Wow. Thank you once again to everyone who continues to follow. It's great. It's amazing.
That's right. Make sure to follow the podcast on Spotify, Apple Music, and go check it out on YouTube. We know there's not that many people that watch it on YouTube, but make sure to go subscribe, leave some comments. We always answer our comments.
Oh, yeah.
And if you have any suggestions, make sure to email us or follow us on Instagram at math.physics.podcast. We'll make sure to get back to you.
Also, for one important piece of news I forgot to mention. Recently, again, if you guys are following our Instagram, you probably know everything I'm about to mention. But if you aren't, then recently, you know how Spotify has its yearly Wrapped session? Mm-hmm. So it also has its Wrapped for podcasters, right? And we saw that our podcast, the Math and Physics Podcast, was top 109 in or science podcasts in the United States.
It's 103.
Oh, 103. Sorry, 103. That's amazing. So once again, thank you to everyone who continues to listen. And we also got one viewer who personally DM'd us where the Math and Physics Podcast was their number one listen podcast of 2020.
Hey.
So that was amazing to look at. Thank you so much.
Shout out to everybody that is enjoying the podcast, and we enjoy making them. So this is a great symbiotic relationship we have here.
Yep.
So now getting into the approximation wars. Okay, So I'm going to be doing the Taylor approximations, and Rehan is going to do the Fourier approximations.
Yep.
Right, so getting into a little bit of the history behind Taylor approximations. So, right, approximating things in general was always a topic of discussion since all of time, all of intelligent time. The Greek philosopher Zeno actually considered the problem of summing an infinite amount of things to get a finite result. So a common idea that we talk about in infinite series is, so you have a square, right? And then what you do is you sum up half of the remaining area infinitely, right? An infinite amount of times. As the terms in your infinite sum go to infinity, you get a finite result, which is just the area of your big square. I don't know if you guys could picture that, but you just take half the square, you add that area, then you take half of whatever's left and you add that, and then half, so on. And so people have been thinking about how to approximate these results for a very long time, but at first it was just rejected. They weren't getting too technical with the calculus, of course, which was invented by Newton. Quick reference to our first history of physics episode, where we covered Newton and Richard Feynman. So yeah, also quick intermission. Make sure to comment who you want us to cover in the history of physics. Do you have any mathematicians or physicists that you really look up to and you want us to cover? Let us know. Anyways, so later, Aristotle proposed a philosophical resolution of Zeno's paradox, but the mathematical content of what Aristotle proposed was taken up later by Archimedes, and it has been prior to Aristotle by the pre-Socratic atomist Democritus. Okay, a lot of big words there.
Yeah, for sure.
So, these approximation ideas were being thrown around for a long time until the 14th century was the first example of a Taylor series. Okay, and so what is a Taylor series? Before we continue on, basically you have a function, and we'll just stick to the one-dimensional cases. We're not going to get into the multivariable Taylor approximations and all that.
Well, two-dimensional, one variable.
Well, no, it's one-dimensional because there's one variable. But anyways, so the one-dimensional Taylor series or Taylor approximation is you have any function, and you know the value of that function at a certain point. But what you want to do is construct a polynomial. And a polynomial is just a linear combination of powers of x. In this case, we're using x as our variable. So the first power is, of course, 0, which is just a constant. And then you have a first order approximation, second order, third order, which are terms that go up to, or whatever power you're considering. So if you want to do a third order approximation, then you will have at most a third power term. And so it turns out you can actually approximate functions very well, and we will get into a little bit of the mathematical ideas after we cover the history, but that was just a brief little overview of what a Taylor series is. So in the 17th century, James Gregory actually published a couple of Maclaurin series, which is just a Taylor series, but before Taylor actually formalized it, right? A Maclaurin series is just a Taylor series centered at 0. So you can center your approximation at any point, but like specifically when it's centered at 0, they're just called Maclaurin series. And so James Gregory, he published a few Maclaurin series, including a few trigonometric functions like sine, cosines, and tans. And he was born in 1638 in Scotland, and he died in 1675. He also had a lot of other contributions in the world of physics and astronomy, but we're going to focus on his mathematical contributions for today. Just a little example, though. In 1663, he described the first reflecting telescope, which Newton actually developed a few years later.
Oh, that's interesting.
So sorry?
Yeah, I actually didn't know that. That's pretty cool. Wow.
Yeah. So he was in the optics game for a while, and also he has a few advancements, right, in trigonometry and calculus, and we're going to focus, of course, on his infinite sums, his infinite series, and his approximations. Before Taylor actually formalized these ideas, he published the ideas that Taylor would then use to generalize and formalize the idea of approximating functions using polynomials. So then we have Brooke Taylor, who was born in, how do you say that? Brooke Taylor, who was born in 1685 in London, England, and then he died in 1731. So he studied at the University of Cambridge, and he is most famous for generalizing the approximation methods of James Gregory. To be a little bit more technical, the Taylor series, the Taylor approximations, are only available to functions that are differentiable, like up to the order that you want, right? So if you want a sixth order approximation, then you will need your function to be 6 times differentiable at the point that you are focusing on, right?
Yeah.
So, and he's also famous for Taylor's theorem, which relates back to these approximation methods. So we're going to get deeper into the actual mathematics and how you would construct these polynomials more specifically later, but I will pass it on to Rehan.
Okay. So that was quite a history, actually, from Taylor polynomials. I did not know it had roots all the way to Aristotle and Archimedes, or sorry, who you were mentioning.
Yeah. Well, technically, the Taylor polynomials were not just being discussed, but the idea of approximating things.
I mean, obviously, because the name Taylor hadn't really been born yet.
Yeah.
So yeah, I mean, I don't think anyone was really saying what's the Taylor approximation for this in 1650, but
Yeah.
it was approximating was an idea. So
Yeah.
So moving on to Fourier approximations. Now, Fourier does not have, or at least the series itself doesn't have much of a history like Taylor does. It's quite short. It's simply that Joseph Fourier simply designed the idea of Fourier series in one of his papers to tackle the idea of heat flow. And I'm obviously going to be emphasizing a little bit more on this, but first let's talk a little bit about Joseph Fourier. He was born on 21st March in 1768, so this was quite a bit after Brooke Taylor, who was born in 1685. And quite a sad story, actually, with Joseph Fourier. He was a son of a tailor and orphaned at the age of 9. He was a big part in the French Revolution at the time. He was imprisoned. He's basically been through a lot in his childhood, and actually even in his later stages, he succeeded Jean-Baptiste as permanent secretary in this Academy of Sciences. He was elected a foreign member of Royal Swedish Academy of Sciences. So there was a lot of things that was going on in Joseph Fourier's life. But something he obviously did extremely well was the Fourier approximations. There were 2 major physical contributions that he made in his field and 1 major mathematical contribution. The mathematical one, of course, is in fact Fourier series or Fourier transforms. The idea that he had, what he claimed, is that any function of a single variable can be written as a sum of sines and cosines of that variable. However, after more, focus on his work and more generalization, people found out that that's not entirely true. It only works for periodic functions. However, something that he completely broke through was that, and something that he didn't even realize, because he was only talking about continuous functions. Something he didn't even realize at the time is that when you sum up these sines and cosines, and you take that sum to infinity, you can approximate a discontinuous function. And that breakthrough, the idea that you can approximate a function that is not continuous, was completely, it was unheard of. Because I'm pretty sure even Taylor polynomials require the function to be continuous. However, Fourier showed that even discontinuous functions can now be represented as a sum of cosine and sine waves. Now, as Parker said, we're going to get into the math of it a little bit later, and just getting onto his 2 major physical contributions. The one major thing he did was dimensional homogeneity, which in simple terms basically is if an equation is valid, if and only if the left side and the right side of the equation, the dimensions of both the sides are the same. The dimensions match. For example, in the most common equation, like F equals ma, force equals mass times acceleration, We have force, which is in units of newtons, and we have mass times acceleration, which is also in units of newtons. So that equation is valid. And this was, I mean, even though it's kind of obvious, to be honest, that if the two dimensions are equal, like the equation is valid, and without it, obviously the equation would just not make sense. But I guess this is some breakthrough that he made. But the bigger one was the solutions for the heat equation. And this is actually where the Fourier series came out of his work. So Newton had studied for a long time the heat equation, and the heat equation is basically a partial derivative equation.
Partial differential.
Partial differential equation. Sorry, small mix-up.
Right.
So as I was saying, the idea is we want to try and solve for the solutions of this equation. But no one could really do that because no one really knew how to correctly express the heat wave. No one really understood because the heat wave is a very complicated thing. People used to simply use a single sine or cosine, but they didn't really know how to accurately represent the function. There comes in Joseph Fourier with his paper on heat flow. And what he does is he states that heat can be represented as a superposition of multiple sine and cosine waves. And this idea of using superposition of sine and cosine waves is exactly what we call Fourier series. So when a function, any function could be, but it must be periodic, of course, any periodic function that is continuous, that is discontinuous, it doesn't matter. With enough sine and cosine waves, we can make any function, is what Fourier claimed and is what Fourier showed through his paper on heat flow. So what Fourier basically did was, I think the biggest thing, once again, just to summarize all of his contributions, was not really that any function can be represented in sine and cosine, even though it has immense modern applications. The bigger thing that I believe he did was, again, approximating discontinuous functions, which is something that no one really had ever thought of. So now we can, I guess, go a little bit into the math, a little bit into the math behind Taylor and Fourier series, and just talk about how we can construct them. So, Parker.
Yeah, and one thing I wanted to just go over, when we say approximating discontinuous functions, it's not that the approximation is discontinuous itself. It's just that it becomes arbitrarily similar. Mm-hmm. Like the error between the Fourier approximation and the actual function that it's approximating, as the amount of cosine and sine terms increases, right, the superposition increases, that error goes to zero. And so the result is that you have a superposition of continuous differentiable functions that is discontinuous at a point, which is not possible, but that is why it's so revolutionary, right?
Exactly.
The approximation is never actually discontinuous, but as you add your terms to infinity, it becomes, the limit as the terms goes to infinity is pretty much the exact same as a discontinuous function.
Mm-hmm. And one thing to mention, I think, on both the functions with approximations is especially with Taylor, when you say order of approximation, and with Fourier, how you talk about the nth Fourier approximation, right? Like that number really matters as to how well your approximation will fit, right? Or how well it will look as compared to your function, or in technical terms, how close the error is or how small the error is. Mm-hmm. So the larger your approximation, or the larger in Fourier terms, or the larger of order of approximation in Taylor terms, the closer your approximation will be to your function. Closer in quotation marks, of course, because technically we were talking about the error that would be a lot less than the lower approximation number.
Mm-hmm. And the difference between Taylor and Fourier is that in Taylor, when you're talking about the nth order, you're talking about the number of powers of x you're dealing with. But in terms of Fourier approximations, the nth order actually represents the frequency at which the sine and cosine terms are oscillating. So the first order is going to be a very general approximation and is going to have a very low frequency or a high wavelength, right? And then when you keep increasing the approximation number, you're adding faster and faster frequencies of sine and cosine terms, which will then in turn give you a more accurate depiction of the function you're trying to approximate. So yeah, should I talk about the math of Fourier series, Taylor series?
Yeah, we can go a little bit into the math in the Taylor series. Let's go.
This is going to require some picturing skills and also a little bit of background calculus knowledge, okay? But I'm going to try to make it as easy as possible. So, for example, okay, let's take f of x equals x squared, right? Just a simple parabola. So, if you want to approximate polynomial, obviously at some point, the approximation is going to equal the function because you're trying to construct a polynomial that approximates a polynomial. Well, eventually you're just going to have that exact polynomial as the approximation. So for example, you want to approximate x squared as a polynomial, you would just pick x squared. But the point where it gets a little bit harder is when you're not dealing with polynomials. Let's say we're dealing with cosine. Cosine at 0 is just 1, and then it decreases on both sides of the origin. So how you would go about creating a polynomial? Well, first you would look at, and we're going to center it at 0, right? So we're going to center our approximation at 0. So the first term is going to be a 0 power of x. So it's just going to be a constant. So how do you figure out the best approximation for a function and all you have is a constant? Well, you would just match the value of your function with the constant. So the 0th order approximation of a cosine is just y equals 1, right? Just a constant function that has the same value of cosine at that point. Now, next up, first order term. The most logical thing to do would be, well, you have the same value of cosine at 0. The most logical thing to do would be to have the same rate of change of the cosine wave at 0. And so the rate of change of the cosine wave is 0. So you would actually be adding nothing as your first order approximation. But as we know, the second derivative of a function tells you the curvature. And so your approximation should have the same second derivative, the same curvature. And so the actual general formula, right, would be, and I'm not going to get too deep into like the coefficients and all that stuff, but the idea is to just match the value of the function and then also match the subsequent derivative values. And there are tons of great animations you can find on YouTube of how, when you keep adding terms, your approximation gets better and better. But it should kind of be intuitive, I think. Unless you've never seen Taylor polynomials before, this can be kind of abstract. But I find it pretty logical when you just match up the values and the subsequent derivatives. It sucks that I can't go over it with like a piece of paper and do it mathematically. I can just explain it with my voice. But that's pretty much the idea.
Mm-hmm. I think paper would definitely help for any kind of mathematical explanation, especially in this regard when we're trying to explain graphically. Mm-hmm. It's definitely a little tough. And I think the same goes for Fourier, because especially with Fourier, when you're talking about waves, it's so much better to look at them and to like truly understand how you're adding them up. So so that's actually why in the link below, I have included a phenomenal website, in my opinion, to help you understand Fourier series. But even if you don't want to really understand it, just to look at what I'm talking about, it would be a lot easier. Because basically what all it's doing is it has some waves, and then it has pictures of other waves. And all it's doing is graphically showing you what Fourier series does, right? So Parker, do you want to talk a little bit more about Taylor, or...
Maybe we could circle back after talking about Fourier.
Okay, so let's start a little bit with Fourier series. So as I said, The idea of a Fourier series is to approximate any function, not using polynomials in this case, much like Taylor, but by using sines and cosines. And the advantage of this is that sines and cosines are waves. And these waves can be represented, or mathematically represented would be better, in many ways. For example, this only works with functions that are periodic. So if we have y equals sine x, for example, right? I mean, it's very easy to approximate that, right? The approximation will just be y equals sine x. But let's say we have something like y equals sine 2x, or y equals 2 sine x. This would actually probably be better. So all we're trying to do here is we're multiplying the amplitude. So what is y equals 2 sine x? The much better way to represent that would be as a sum of two separate sine waves, y equals sine x plus y equals sine x, right? When you add them together, you get 2 sine x. Now, obviously, that was a very, very, very easy example compared to what we usually do with Fourier analysis, but that kind of gets you the intuition of what Fourier series truly does. It takes any periodic function, and in this case, I just gave you a wave, any periodic function, and it can represent that as a sum of other periodic functions. Now, to get a perfect approximation, when obviously things are discontinuous and things like that, we must need an infinite number of these sines and cosines. But obviously that is a little bit of a stretch. But now we're just going to be talking a little more about just finite sines and cosines and what they can look like. The most, or at least the most useful application for this in today's world, for example, is just strings on a guitar or harmonics, right? Every note is a composition of other notes. If you think about plucking any string on a guitar, right, and you represent that mathematically, it would simply be a sine or a cosine wave. Well, it doesn't matter, right? It would just be some kind of wave. Now, that wave can be a sum of other waves, just like Fourier stated. So, what does this say? This says that any note on the guitar, for example, let's say I pluck a string, can be represented as a sum of other notes. That means one note can be played with, let's say, 10 notes. 10 different notes, when they all come together, they sound like that one note. And that's basically the idea of Fourier series and what Fourier did. Now, obviously, in the way that he applied it was very, very different because, as I said, he applied it in the heat equation, and that's actually where it arose from. But we're not really going to be talking about the physics of it. We're mainly going to be just focusing on the math, on like how Fourier series really transforms something, right?
And Ray,
yeah,
not only that, right? You're talking about just guitar strings.
Mm-hmm.
Any sound can be approximated by like a superposition of sine and cosine waves. Like, for example, in one of our first problem set that we did was actually on Fourier series.
True.
And we had to like listen to videos where they would show us the sound wave, and it would be like some complicated wave, or for example, they'd show us like I don't know how to describe this, but it's like a square version of a sine wave.
Mm-hmm.
Right? Like, instead of being all curvy, it goes from like -1 to 1, but just as a straight line, and then from 1,
like a triangular wave, there's a square wave.
Yeah. Oh yeah, triangular wave. There you go. So they would show us a triangular wave, and they would play the sound of that triangular wave, and then they would play the sound of each wave that gets superposed to create that triangle wave, but then they play them one at a time, and they construct the weird sound of the triangular wave one by one by adding them, and then slowly you can hear the sound of the triangular wave like arising, but slowly, right? So you start with like a weird, like just a regular note.
In the beginning, it's always like it sounds like absolutely nothing.
Yeah,
because as I stated, that's a first order approximation, or in Fourier terms, it's a first Fourier approximation. So the first order of anything, and if you're approximating it, is very, very, very sad. It's nothing that really seems like what you're trying to approximate, right? But as you get deeper and deeper and deeper, and you increase that value of n, or So as you increase that value of n, you get a better and better approximation to the function, or to the wave in this case.
I thought that was really cool because we're used to seeing like visual evolutions of approximations, right? Like we see this wave, and then we add another one, and we add another one, and we're like, oh yeah, it gets closer and closer to the function, okay? But now we actually got to understand how a superposition of waves can result in this weird, this weird triangular wave. But we got to understand it audibly, right? Like we heard what the regular sine wave sounds like, and then a different wave, and then a different wave, and then all added together, they get closer and closer to the actual sound of this weird, like undifferentiable wave.
Yeah. So getting or continuing on with the Fourier series, we have a very, very interesting part of Fourier series, something you can do with them. Create images with Fourier series, or what is usually called Fourier transforms. So usually, to be honest, the notation is kind of blown away everywhere. Like sometimes I hear Fourier transforms as transforming a function into a sum of sine and cosines, and sometimes I hear Fourier transforms as transforming an image into a sum of... So it's basically when you're transforming anything into a sum of sines and cosines, that's a Fourier transform. So the idea of a Fourier transform is basically three-dimensional sine waves. Now, once again, the website that I linked below will explain it so fantastically because this is a kind of a very visual explanation. But basically the idea is, think of a spring, or as Parker was trying to explain in a previous episode, a helix, right? Which is basically a spring and in this case, the sine wave is moving through time. So the spring is simply kind of rotating forever. That's the basic idea. Now, if you look at the spring from one side, right, it looks as a regular sine or cosine wave. It just looks like the periodic oscillating up and down. But if you look at the spring from head on, it looks like a circle. It looks like a circle that's going round and round its radius, right? The idea behind, again, Fourier series is constructing these infinite, or not infinite, but lots of these sines and cosine waves. So when we get to increasing the number of these sines and cosine waves, and we model it through time, now this is where it becomes important. We model it through time, we can stick all of these circles that are then created. Remember the circles that we see from head on? So if we stick all of these circles on basically a piece of paper stacked on top of each other, that is called an epicycle. What an epicycle actually is the center of a circle that moves around the circumference of another circle. And that's the entire idea of epicycles. The more circles you have, the more circles rotate around these circumferences, and that's the entire idea of Fourier transforms. Let me explain. So let's say we have a first Fourier approximation. In this case, right, the approximation is simply going to be a sine or cosine wave. So it's going to be one wave. And remember the description on the 3D sine waves moving through time? If we look at it from front on, it looks like a circle. So let's put this circle and let's center it at the origin, right? So this circle has some radius and it's centered at the origin. Now, if we draw a vector from the center of the circle to its circumference, and we let the vector move through time, what will it do? Well, it will just, move around the circle and will draw out a circle. So if we draw the tip of the vector, what will it draw out? It will simply draw out a circle. And that's simply because the first Fourier approximation is very, very weak. So let's move on a little further to the second Fourier approximation, and hopefully this will be able to kind of drive the point home. Now we have a second circle. Now I'm going to call circle 1 the circle corresponding to the first Fourier approximation, like the first sine cosine wave, and circle 2 as the second Fourier approximation. So circle 2, the center of circle 2 will now be situated on the circumference of circle 1, right? Because this description is of an epicycle. remember, there is still that vector that is from the center of circle 1 to the circumference of circle 1. Now that we've put the center of circle 2 onto the circumference of circle 1, what can we say? We can say that this original vector is now connecting the center of circle 1 to the center of circle 2, right? Much like circle 1, circle 2 will also have a radius vector, right? A vector that is from the center of circle 2 to the circumference of circle 2. And this vector will move at some speed when we are moving through time, right? Now, the interesting part of these two circles is that we have two vectors as well. One vector connecting the center of circle 1 to the center of circle 2, and vector 2 that connects the center of circle 2 to the circumference of circle 2. As we move through time, both of these vectors kind of move around the circle, right? Vector 1 moves around circle 1, and vector 2 moves around circle 2. But remember, they're always connected to each other, tip to tail. So, what we draw out is now vector 2, the tip of vector 2. So this looks a lot different from what circle 1 simply made. Remember, circle 1, when we traverse the vector, it simply made a circle, right? But when we start moving a vector in circle 2 around circle 1, we start seeing various different shapes depending on the speed of both of these vectors, right? Depending on the shape, depending on the speed, obviously not the shape of the circle, because the circle is in fact a circle, but it depends on how big the circle is, how small the circle is, the speed at which the vector is traversing the circumference. And that's basically the entire idea of Fourier transforms. When we add more and more of these circles, we get into the third, fourth, fifth, sixth Fourier approximation. And there comes kind of like a point where after that point, you basically get the image itself. And that's kind of like the perfect Fourier approximation. So hopefully that helped visualize a little more on Fourier transforms and how Fourier series can be used to literally draw any image simply with a sum of sine and cosine waves. If you go to the website, all the way at the bottom, you can create your own image. And what the website will do is literally create these circles and show you how it would look if we transform this image into a sum of sines and cosines. So again, this website that I'm going to be linking is basically what I'm looking at while I'm talking. So I guess that's why I'm kind of describing it the way I'm seeing it, but I'm also forgetting that no one else is really seeing this right now. So that's definitely a much easier way to explain Fourier transforms, because how else would you explain transforming images? You know, like you kind of need a visual aid. So I don't know if that made sense. I really hope it did. Again, if it didn't, we have it in the link below.
Yeah, we're gonna put some YouTube videos that you guys can go watch. A couple resources.
Yeah, for sure.
But yeah, I think that that concludes our episode on approximations. Was there anything else you wanted to say?
Not really. Just basically the battle of the approximations. The moral of the story is that neither of them are better. They're just for different things. They can be used to represent different functions. As I said, discontinuous for Fourier. And obviously, it doesn't have to be periodic for Taylor, which is quite a difference sometimes.
That's right. And Taylor series are really nice to work with because polynomials are, quote unquote, nice.
Yeah,
right? Like,
that is true.
That
is true.
You can differentiate a polynomial everywhere in an infinite amount of times. Polynomials are all continuous everywhere, and they're easy to work with in general. So if you have a difficult function, but you're just trying to look at a neighborhood around a certain point, it might really be easier to just convert that function into a very well approximated version of it that is just made of polynomials that you can differentiate. You can easily look at the gradient and all that stuff. So yeah, Taylor approximations. Very good. Approved by the Math and Physics podcast.
Hopefully the Fourier made sense to some people. I really hope it did, because, I mean, it was making sense to me as I was saying it, but again, that's because I was looking at what I was talking about, right?
To be honest, it didn't really make sense to me, but I already know what it looks like, so it's easier to...
Yeah, so I guess you're not a very subjective viewer either. So that's why I'm saying, I mean, it would be really great if you just kind of saw this quick snippet of the website in the link below and just saw what I'm talking about. Because the moment you see these circles inside these circles, you'll completely understand my explanation. It's just that seeing this visual, I think, is quite important to understand Fourier transforms. Because without it, it's definitely very hard to explain it, or at least in my opinion.
All right. Thank you, everybody, for tuning in once again. Another week here on the Math and Physics podcast. Go follow us. Ask us questions, recommendations. We have an Instagram at math.physics.podcast. We also have a Facebook page. Same handle as our Instagram. We also have an email. Same thing again, but you add at gmail.com at the end of it. You can also follow the Spotify, subscribe to the YouTube, and also subscribe on Apple Podcasts or Podbean or anywhere else that you are listening to this right now. I think we're on iHeartRadio too.
What? Didn't know that.
Yeah, we're also on Amazon Podcasts.
Oh, what? Amazon has a podcast? That's something I did not know.
I think it's like Audible.
That's cool. That's cool.
Because Amazon owns Audible, but
Yeah.
that's besides the point. The point is that if you have any suggestions, we will look over those suggestions. We will do our research.
Gladly, we will reply. We will reply to all your emails.
We've had a recommendations to talk about neutrinos, but to be honest, I don't know anything about neutrinos, so it would require...
I mean, we can have a quantum mechanics episode, like where we talk about like the standard model, and neutrinos will be a big part of that.
Sure.
You know, like we don't have to make an episode completely on neutrinos. We can just filter it in.
Yeah, I'm very open.
If you guys want a quantum mechanics standard model episode, like email us, inform us, because we would be very, very happy to do that.
That's right, that's right.
That would be really cool.
So, the Math and Physics podcast officially sponsored.
Oh.
That is great. We are also in the works of getting sponsored by other companies. That would be great. All
Yep.
the money we make, we are just going to reinvest.
That would be great.
Make the podcast better. Make it sound nicer.
Yeah.
Make it more interesting. I don't know how money would help that, but, you know, maybe it's going to motivate us to do more research. Who knows?
Maybe.
So, yeah, thank you for listening. This has been, oh God, what episode? 38 now?
38.
Episode number 38. The Battle of the Approximations. I'm your host, Parker.
And I'm Ray, and we will see you soon.
See ya.